surface energy. And we know that by changing that surface energy, we can generate lateral forces. Okay, so here, again, for flying and swimming, you can rationalize this by in a number of ways. So you can rationalize propulsion. You basically generate a flow, and the mean hydrodynamic force, which you get by integrating the normal component of the stress tensor over the surface of the body, has to be non-zero throughout a cycle. So you can basically calculate the flow generated by moving, and as long as that in a time average sense is non-zero, then there'll be a propulsive force which drives you forward. You can also think in terms of momentum transfer. So if you can throw fluid backwards, then you can propel yourself forward. So that's basically, if you have a hovering bird, if a bird is hovering, it's basically flushing air downwards, and the momentum flux associated with its wing motion allows you to rationalize the vertical force on it. Similarly, so when fish swim, there's often a coherent chain of vortices in their wake, which are transferring momentum backwards. Okay, so you can, again, rationalize motion either through looking at the hydrodynamic force acting on the body or the momentum generated. This is generally the latter being true for high Reynolds number swimming. Okay, and so we've seen this before. We know that creatures which are small relative to the capillary length can have their weight supported. So these creatures are always heavy relative to water. So they would sink in the absence of surface tension and in the absence of their water repellent feet. So again, you can compare their weight to the surface tension generated by adding up the contact lengths and see that when they can, if they're small enough, they can reside at rest on the surface. If they're too large, they have to generate forces by hitting the surface. Okay, so small creatures, I think we've seen this before. If they're small enough, surface tension can support them. If they're on this side of the line, they have to hit the surface and rely on dynamic weight support. Okay, so there are other interesting scalings. So these are our friends now. The bond number, so this is a bond number based on leg size, and this is a Weber number. So we can see that the bond number scales like the Weber number. This is for all water walking creatures. Why would that be? Don't know. Here we see how does the Reynolds number scale with Weber number. It seems to scale pretty nicely with Weber number to the 3/4. So this is just looking at all water walking creatures. We just basically evaluate these numbers by looking at the biology data. And you see these scalings emerging, and it's natural to ask, why is that? And so why is that? Well, if we look at these relationships between, so this is just empirical fact. This looks like this looks like this. This is satisfied if the leg speed goes as the creature size to the 1/2. Okay, so this is something which is known to be true for birds and fish. And so, given that many of these things have perhaps evolved from birds and fish, it's perhaps not entirely surprising. But this is just a sort of this is really a rough hand waving, but I think kind of interesting. Whenever you see these scalings emerging, it's natural to ask why, right? And this, we don't really know why, but we know that it's consistent with something which appears in other areas of biolocomotion, which is the speed of a creature scales as its size to the 1/2.
So the speed you're using for your Reynolds number is the speed of the fluid displays, or
it's basically the speed of the creature.
Oh.
Yeah. The speed of the creature is always about the leg speed. Okay, so now we can think. Now let's try and look a little more rigorously at this problem. So this is, again, if we look at lateral propulsion, we have to integrate the normal component of the stress tensor over the surface in contact with the fluid, because here hydrodynamic forces are acting, both viscous and pressure forces. And then we have this additional term, which is the contact force. And we've seen that the surface tension force, we can think of in terms of a curvature pressure and a Marangoni stress. But really, it's just the integral of the line tension around C, right, around this contact line. Okay, so, and for high Reynolds number motion, we can write down time-dependent Bernoulli we can, from that, get the pressure, substitute the pressure in there. Then we put into the stress tensor, then we put the stress tensor in there, and we can look at all of the different components of the hydrodynamic force, or of the propulsive force for an object hitting the surface. Okay? So you see that there are components associated with buoyancy. So if you generate a cavity, if you hit the surface and generate a cavity, there's a hydrostatic pressure against which you can push. Then you have the form drag. So this is the force you feel when you drive in a car and stick your hand out the window. You feel a force proportional to your speed squared and the density of the air. So this goes as the density of water. And then this is a reaction force. This is, again, an inertial force associated with the fact that you're accelerating fluid out of the way. Then you have a viscous drag term. Then this curvature term. We've seen that things can reside at rest on the interface because of the trampoline-like nature of the interface. You can also, if you generate an asymmetric meniscus, then you can generate a propulsive force. And then we have our Marangoni stresses. And the reason, so you write down all of these things, and the nice thing about biology is you write this down and you say, oh, well, that's a mess, right? And so as an applied mathematician, you say, well, let's scale, right? So what we do next is we're going to scale, and we're going to look to see which of these terms is important. And what happens in biology always is every niche is filled by some creature. So if there's some force that can be used by some creature of some size, it will use that force, right? And so it's sort of a paradigm shift. As a mathematician, you're trying to simplify things. And in biology, they're just trying to make use of every conceivable mechanism. Okay, so we're going to classify now water-walking creatures, not in terms of their evolutionary origins, but in terms of their dynamics. So how, which forces do they use to propel themselves across the water surface? Okay? So this is the basic picture that emerges. There are basically four types of propulsion. First, the large creatures, which can't, they're too large to be able to rely on surface tension. They use mostly inertial forces, so basically slap down vortices, and then they can also use the hydrostatic force by pushing against the back of the cavity that they form. And then we see these creatures here, which use mostly inertia and surface tension. These guys we'll focus on. We've seen them once before, but these ones that move by grabbing, distorting the interface, and then we have the Marangoni swimmers. So for these large creatures, basically how do you understand roughly what's going on? Well, they have to generate enough hydrodynamic force to bear their body weight. So basically, if they're hitting the surface with a speed u, then rho u squared over their leg size, in some time average sense, has to be greater than their weight, right? So that's the basic requirement for these things. And of course, doing so, there are associated power requirements and also dynamic stability, which you can use to rule out human beings as viable water walkers, but we'll come to that in a moment. But these guys are pretty good at it. I know you've seen this video before, but it never hurts to see it again. But they're large, and they can float because they have feathers, but they can't float by standing on their feet, right? So they sprint along and generate these large forces. And again, surface tension is not important. We've seen this guy as well, but never hurts to see him again. And this guy, again, too large to be able to rely on surface tension, so it generates large dynamic stresses. It runs at about 15 meters per second. And the associated dynamic stresses can keep it on the water surface. And so here's a nice lab shot of that. So you can see it generating the cavity there. And it pushes against the back of the cavity, right? So in pushing against the back of the cavity, it's actually getting an additional thrust from the hydrostatic. So it's getting a hydrostatic pressure boost. Okay, so the natural question that arises, what's the largest creature that can walk on water? And corollary, can man walk on water? And so you can ask, I don't know if this was on your first problem set, but it certainly should have been. So right, so we saw that perimeter of your feet has to be extremely large, like on the order of 10 kilometers. So option 1, so that's using surface tension, so a bad idea, right? Option 2, run via slapping. So if you just do this calculation, then you find that your feet have to be on the order of 1 meter, which is kind of large, but not that big, right? I mean, you can imagine putting on clown shoes and having it go. One of my students actually is really good at designing things, and he tried doing this. It didn't work. But so Glashing and McMahon looked at this problem, and they decided that a man would need to be able to run 30 meters per second, which is 3 times faster than he can, and generate 15 times as much muscle power. Okay, so we're not strong enough or fast enough to do it. And also there's the question of stability, like balance. So these lizards have long tails and so forth. So. But nevertheless,
a few people have tried it. Nobody has ever managed to get any.
Have I shown this to you guys? I don't think I have.
You can do these things. It's not like impossible. There's been a few people that have been like sort of following us. It's
me, my boots and I, we're going to make it.
I definitely think it's going to be the next big thing.
It's going to be the next big thing, he says.
The liquid mountaineering is actually a Oof's brainchild.
New sport was not existing before. You have to run very fast on the water.
I mean, obviously the first step was the most important one. When we discovered, oh my God, Jesus, we're going 1 step, we're going 2 steps, we're going 3 steps. We're discovering it as we go along.
While we're still on land, we try to get up really speed. Soon we touch the water. We try to get like a swimming machine. It's not straight into the water, in a curve, in a slight curve.
And by that bend, you're actually not allowing yourself to sink into the water, and you want to keep that skimming sensation going as long as you can.
What a bunch of rubbish. But
what gets us those extra steps are these shoes.
They clearly have platforms just below the water. You can even see when they hit the surface, you get a sheet of water.
We found some shoes by mistake, actually.
Totally water repellent. It's like water off the duck's back.
Oh, come on. You guys know this, right? Water repellent shoes are not going to help you.
It takes actually a lot of practice, a lot of focus.
You might get an air bubble around your shoe as you sink. But watch carefully the surface of the water. You can tell that it's a hoax. Because the waves act differently as they go over. So you can see on that one. Yeah, look at, you can see where the steps are because the waves are breaking differently.
We've been working on a jet ski system, obviously that pulls it into the water with a bit more speed.
Be with yourself, believe in it.
Believe in it.
It's not about the miracle, it's just go for it.
Try to do it. If you fall down, try again.
People want you to think in a certain way, and this sport actually allows you to push your horizons further. It's not boxing you in and saying that's where you are. You're just you're moving past it all.
So the press contacted me, and that was my comment. So I thought it was fairly good. I said, "Do not waste my time." Right? But don't you think it's possible? No. So in any case, so humans need flotation devices, right? So ninjas have been something called Mizugo ninjas were trained to walk on water, but they would have flotation devices, and this is also envisaged by Da Vinci. And someone did have water walking skis and walked from Europe to Barbados or somewhere, across the Atlantic. But this is actually the biggest creature that can walk on water. And they're kind of interesting questions here, because you can ask, how does it do it? And you can, so basically the force that any creature can generate scales as its cross-sectional area. We'll see that a little later in the lecture. And its weight goes as L cubed. So we expect smallest fish are most likely to be able to tail walk. But in order to stabilize something, you know, it's very hard to balance something like this, right, on your finger. But it's very easy to get something longer. It's easy, right? And so there's actually going to be an optimal size at which you expect this sort of motion to be stable. Okay, so they've got to be small for weight support, large for stability. But never quite finished that one off. But anyways, okay, so that's on large things walking on water. And then we've seen some examples of this. So we've seen Marangoni propulsion many times in the course, where you just change the surface chemistry and so propel yourself forward. We've seen this video before, but that's exactly what this bug is doing. So it's generating tangential stresses by altering the surface tension chemically. They actually use this technique. So if there's a spill of some unfavorable chemical, then they'll lay down tracks and they'll follow each other over the clear areas. Okay, and then these quasi-static guys. So the meniscus, so these again don't rely on dynamics, they rely on chemistry. These guys rely on deformation of the surface. And again, these guys can climb menisci and so forth to escape to land. And so many creatures can just jump over menisci or reach over them. But if they're small, such as this baby water strider, they can't. And so they rely on the Cheerios effect, which we've been through. But basically, the system is acting to minimize the anomalous surface energy. Okay. So we've seen this also. We can rationalize the force on two floating objects by writing down the gravitational potential energy plus the surface energy of the system, and so calculate the force as a function of distance. And that's what's responsible for the attractive force between objects floating on the surface and also between these bugs and whatever they're approaching, the meniscus. And if you could write down simply the surface, the shape of the surface at all for any given positions, you could calculate the force on these objects. Okay, and so this is what's used by this guy. So it arches its back and so climbs up the meniscus. So it arches its back so that its back matches the curvature of the meniscus, and so the anomalous surface energy, which is here, is released as it climbs. Okay? And that energy exceeds the gravitational potential energy of its climbing. So again, by arching its back, it's creating this anomalous surface area and anomalous surface energy, which is released as it climbs here. Of course, the gravitational potential energy is greater, but that can be less than the surface energy, and if it is, then it will move. Okay, so, and then these guys we saw can cling on to the interface, and so generate menisci which are attracted up the background meniscus. And you can see how this works. Here you see them grasp. They actually have, so we've seen most of these bugs are water repellent, but these guys have retractable claws which are hydrophilic. So they dip into the surface and then pull up. And so that generates the meniscus here, and these menisci are drawn upwards. And they also have to pull up with their back legs to balance the torque. And they need to support their weight also, so they're pushed. So they have the retractable claws are there and there, but they have water repellent central feet which support their weight. So you have to support weight and balance torques. So this is basically the picture, again pulling upwards here to generate the lateral force, pulling up here to balance torques, and pushing down here. Okay, Okay, and so this is a video and we light from above so we can see the surface distortion reflected here. So you pull up, you focus light, you get these white spots. You push down, you get dark spots. Okay, and so this is also used in so attracting mates at the surface. So these guys decide they don't like each other. But so if you have a colony at sea or in a pond, they want to stay together. They want to group together, so they basically can form, lock into these shapes, which will cause them to group together.
So these are not water repellent, or do they have the same shape?
These guys here have little fixtures. I'll show you in a second, which allows them to distort the surface. Yeah, they have to have something which is non-water repellent in order to distort the surface. Yeah. So. Okay, so we'll come to that in a second. So the great majority of water-walking creatures, such as the water strider, are water repellent, and they nevertheless propel themselves across the surface. So they have hairy, non-wetting legs, sort of scale. They're about 1 to 10 times the size of a mosquito, around a centimeter in length, and their perimeter is around 5 centimeters. So if you look at their life cycle, they spend most of their life, they're basically born underwater, they hatch from eggs, and then they swim towards the surface very inefficiently. It's like, if you can imagine a rowboat functioning as a submarine, that's sort of what it looks like. It's very inefficient, so they sort of make it to the surface finally, then they break through, then they spend their whole lives on the surface, and then they have to lay eggs across the surface. So basically, they're hatched underwater but spend their whole life on the water surface. And this is, you can see this propelling itself, so they can basically drive themselves vertically or horizontally by slapping the surface. So moving their legs in a rowing motion. Okay, so there we saw the thing really take off. And there you can see its vertical leap on water, and you can ask, well, what's its vertical leap on water compared to its vertical leap on land? You see the landing wasn't so good. Yeah, so it's about the same. So they can jump about the same height on water as on land. And so basically what we did is we did the first flow visualization experiments on these creatures. So we basically looked to see what sort of flows they're generating in the underlying fluid. Okay? And so just by looking at them, you can make some inferences. So the Reynolds number based on the stroke speed is high. Okay? So we don't expect viscosity to be important. So they're moving at very high speeds, around more than a meter per second. The propulsive force is around 50 dynes. Okay? And if you and so you can get this by either measuring its acceleration or its height, its leap height, right? It's basically applying a force F over a distance L comparable to its length and going up a distance H, so you can infer then the force. And so you see that this is basically ideally tuned to life at the interface because its length is around, its contact length is around a centimeter, right? So it's generating this as large a force as it can without actually breaking through, right? Because if it hit with a really large enough force, it would break through the surface, right? So it's sort of a tune to generate as large a force as it can without penetrating the surface. And so this is an infant water strider, and this is what got me into this. Is I read something by Mark Denny, which is suggesting that there was that it was a paradox as to how these things move. So this was the Denny's paradox as stated. So how they manage to propel themselves across the water surface remains a mystery, these infant water striders. So the reasoning is that the momentum was transferred exclusively in the form of waves. So the physical picture is that these things hit the surface and generate waves, and these waves carry momentum, which then propels them forward. Okay? And then further, it is true that if you move at too slow a speed on a surface, so if you have steady flow past an object, it doesn't generate waves unless the flow is fast enough. And there's a critical speed, which is around 23 centimeters per second, at which you generate. So if you just drag an object across the surface, you don't generate waves until you hit this critical value. So the question was, how is it that these infant water striders generate the waves required to propel them forward, okay, when their leg speed is less than this critical value? Well, so there are a few problems with this reasoning. One is that this is true for steady motion, but not unsteady motion. If you have unsteady motion, you can generate waves. But beyond that, waves aren't necessary for propulsion. So that was an infant water strider who's not too concerned about the paradox. He just zips along the surface. And you can do flow visualization. And the flow visualization indicates that it's generating vortices in the underlying water. And so this is made clear here, where you see it basically strokes across the dye line, and you can see it's generating a pair of vortices, right? And these are sufficient to propel it forward. So the momentum generated in the vortices is greatly in excess of that in the wave field. Okay, and so here's the images of the vortex pairs. So this is an infant water strider, this is an adult, but again, with each leg stroke, it's basically generating a pair of vortices which propel fluid backwards. And this is our more arty form. So you'll understand, we've seen Marangoni convection in the course, right? So basically what we do is we sprinkle the surface with thymol blue, which is a chemical, and it changes the surface tension. And so the surface goes unstable to Marangoni convection, which is why you get these are basically little convection cells. So that's what gives you the texture. And this is a big chunk of this material. So it decreases the surface tension and you get this surface divergence. And so that clears the surface. And these things swim towards light. So you light it at the table from below, and they always go towards the light regions. Okay, so you can see how we resolve Denny's paradox simply by looking at the system and seeing that the momentum is transferred principally in vortices rather than waves. And so you think of these things then rowing using their legs as oars and the menisci as blades. They basically have to hit the surface not too hard or they'll break through the interface. As long as they can maintain the meniscus, then they'll be fine. Right? And this does rely on their water repellency, as we'll see. Okay, but that sort of puts these things in context with birds and fish, which have a coherent vortex structure behind them. So do these water-walking creatures. Okay, and this is true. So all sorts of these bugs have coherent vortical wakes. Okay, and so it's kind of fun something we like doing is once we figure out how something works, then we try and build it and see what the technical difficulties are. And so this is we tried to make the first water-walking robot. And so we knew it had to have non-wetting legs. We didn't then know too much about water repellency, so we just made it out of stainless steel. And then we know that it had to be light enough to be supported by surface tension. And we knew that the driving force had to be less than 2 sigma or it would break through the surface. And we wanted to have something which looked like a real water strider. So this is it. Is the Robo Strider, and this is its natural counterpart. So it's about 10 times bigger, but it's so it has an elastic thread, which my student is a thread from his sock, and this is made out of this lightweight aluminum chassis was made from a 7-Up tin, so it's very light. And then you have these stainless steel wires which keep the thing from sticking. And so here it is, and it worked. I think this is the best it ever worked. Got 5 strokes. But you see it moves itself along the water surface. And so that was the first one. And then that, of course, once we'd done that, then all sorts of people started building these. I'm not really sure why, but it was so there's been a subsequent fleet of water-walking robots. We just did it for fun. But so these guys are engineers, so they have to argue about its importance. What is it? Yeah, I'm not sure. I shouldn't go into it. But yeah, there has been a generation. They're talking about solar-powered water walking. It's a tough sell, but they. The other thing in our lab, we like doing things which have just like made out of junk. So, and like in terms of return for the investment, and there was no investment. So this was literally made out of junk in the lab, and it was written up in the Economist. So that was good impact value. So so we see basically we rationalize how all of the various modes of propulsion for water walking creatures we've seen. So there have been subsequent to our study of water striders, they did some flow visualization on these lizards, and they found that they too generate vortices. But the vortices there also are responsible for weight support. So they have to have a vertical component, right? So they have to go down to support the weight. Whereas these water walking creatures use surface tension for weight support, but for propulsion, they use these vortices. Okay, okay, so then this got us interested in what was happening on the microscale. So then we had to learn about water repellency and contact dynamics and so forth. And this then opened up a whole new channel of research, because there are many peculiar problems in biology which involve contact lines, moving contact lines. Okay, so again, we've seen that the secret to water repellency, water repellent surfaces, again stolen from nature, is that they be they have a hierarchy of roughness, and they be water repellent. So the combination of water repellency, the contact angle has to be greater than 90 degrees. If that's true, and you have a rough surface, then the surface will become extremely water repellent, and that's the case for water walking creatures. So water walking spiders look like this. Terrestrial spiders look like this when they're wet. So here you see water beating up. So they're clearly water repellent. And these guys, the water coats them. So these things have basically adapted to life on the interface by virtue of their surface coating.
Is that maybe used for drinking for the land spiders?
Could be. There are things that, so you guys just looked at drops moving on tapered. No, it's definitely used in nature somewhere. I think there's a cactus. So cacti use this in the desert. So they basically have these needles, and water will condense in the morning on them, on their needles, and so then the water will actually move in response to the change in the shape of the needles. But yeah, I'm sure if not this one, there is some bug that uses it somewhere, right? Okay, so here with some more images. So this is fisher spider. So you can see here you have this sort of textured surface reflecting this texture of the object, but it's basically in a Cassie state, right? So so all of these things have to stay in a Cassie state. Right? So if they don't, they're in big trouble. Okay? So again, we've seen this picture before. These guys are basically covered in fine hair, and they're waxy, and so and this roughness in combination with the waxy surface makes them super hydrophobic. Okay, so this is, I think I described this, but I didn't show you the gory images. So this is what happens if you put a drop of soap on a water surface with a water strider. So normally they reside at rest. But if you put in soap, it changes the wetting property. So it changes the contact angle from more than 90 degrees to less than 90 degrees. And then when you cross that line, things change qualitatively. So suddenly, if it's less than 90 degrees, it means that these things are hydrophilic. And so the water just soaks into their surface coating, into their hairy legs, and they just sink through the surface. Right? And so when you think about it, this is a real problem, because these things weigh around 5 dynes, and the force required to cross the interface is basically their contact perimeter times 70, so it's around 500. So basically they have to create 100 times their body weight to cross the interface, right? So it's something which is not easy for them. Of course, it's easier if they're surfactant, so it brings the surface tension down. But in any case, so if these things get wet, as happens here, or sometimes they get nailed by a raindrop, then they basically go onto land and they groom, they clean themselves up, and they wait till the water evaporates. Okay, so surface coating has two forms. So on the legs, it looks basically like this. You have hairs pointing towards the tip of the leg, and then on the body, you have this these long hairs, which are like these ones, and then you have this mat of very fine hairs, and these these allow the thing to breathe if it's submerged, because basically water can never penetrate into there, well, unless you get to ridiculously large depths. But it's these guys that allow, so it's this fine hair on the surface of the body which allows them to breathe. Because they breathe through spiracles, which are basically portals on their body cavity, and so provided the water doesn't penetrate there, they can continue to breathe. And so we showed you this before. These things can stay underwater indefinitely, breathing through this air bubble. So again, for these guys we saw walking on the water surface, they're saying, oh, but our shoes are water repellent. Yeah, so they might, at best you have a bubble of air on your shoes. But anyways, by looking at the plastron chemistry and the mechanics, you can find the range of depths in which they survive. So basically the geometry of the interface sets the area of the lung. So if you go to greater depth, you can actually have a larger surface area of the lung, so you can breathe more readily. Of course, then there's a limit, and then when the thing touches down, then you're going to drown. But you can basically get an idea of the range of depths, and it's going to depend on your metabolic rate. So in the winter, when they move much less, they actually operate in different depths within the water column. Okay? And then you can look at, so some of these guys will actually trap bubbles and use that for breathing. You can only survive in flowing streams, which is kind of curious. But then I think we mentioned the human equivalent. You can make a big diving bell. But again, you have to keep it. The whole secret here is keeping the things clean, and this is why bugs spend much of their time grooming. So the water-walking creatures, as well as these underwater breathers, they're always grooming to keep their water repellent surfaces clean. Okay, so if you look now at the microstructure of these legs, they have, so this is the sort of big picture. If we zoom in, these hairs have, this is an individual hair now, so it also has texture on the scale of around 100 nanometers. Is that right? 3 microns? Yeah, something around there, hundreds of nanometers. But you basically have texture. So this is the leg, then you have the hairs pointing in this direction, then on the hairs you have these longitudinal grooves. Okay? So the key thing is that these guys are indeed in a Cassie state. So they only make contact through individual hairs. So the water doesn't penetrate into the roughness. So these are the first images of these guys, and so you can then rationalize how these guys can run across the surface without getting wet, and they can detach quite easily from the surface. So here we see this fisher spider running across the surface. So its leg penetrates, but its leg remains unwet. So water doesn't penetrate into its surface coating.
It's like it's pushing back with the hydraulic pressure too.
Yeah. Yeah, probably. Yeah, these guys are pretty big, so it's probably true. So, but again, you can see the thing leaping off the surface without, there aren't any drops flying anywhere, so it's basically getting a clean release. And so the question is, can these guys maintain a Cassie state, or can they not? Right? We've seen that the key to sort of clean release, so the key in designing water repellent surfaces is maintaining a Cassie state. So the question is, what's if we have a rough surface and we hit the surface in order to generate propulsive forces, are the associated pressures high enough to cause penetration of the roughness? So this perhaps isn't the best image, but you can imagine we have some roughness elements, which is basically the hair, and there's a characteristic length scale. And we know that there's a dynamic pressure scale, rho u squared, which is causing impregnation. So if this Weber number is too high, then things are going to get wet, but if it's small enough, they won't. So we see that basically, and we expect the crossover to be around Weber number 1. So we can see that all of these water-walking creatures, the insects and the spiders, have Weber number much less than 1, which means that their coat is sufficiently dense to keep them from getting wet. And again, if they do get wet, it's a real problem, right? Because then they sink through the surface because they are heavy relative to water. But these big guys who don't really care about surface tension, they don't care so much about getting wet. But and so it turns out, so this is a high pressure, but these guys are all designed. Basically, their coating is designed to keep them in a gassy state as they walk on the water surface. The largest pressure they ever encounter is the dynamic pressure from raindrop impact. So that's something, I think looking at their behavior in rain is kind of an interesting problem.
And if you have platypus there, does he strike through?
A platypus, so these guys dive,
Oh.
and they will, so these guys, I think they trap air in there. They have like quite long coats, and I think they trap air. I think bears do like polar bears. So I read something on part. So they have a sort of, it's like a wetsuit, right? Because you imagine if a polar bear gets wet, the water is cold, right? So it's basically going to lose all of its heat incredibly quickly. But if you maintain an air layer, then you can conserve your heat. And so they talk about them basically having dry suits. So their fur basically traps an air layer, and so they can swim without losing their heat. So. Okay, so, right, so again, much of the sort of function of these water-walking creatures, so their propulsion, their maintenance of a gassy state, so either for staying on the water surface, or for the case of these underwater breathers, breathing, these rely on their surface being clean. And so these guys spend much of their time grooming to maintain their water repellency. Okay, and so there is a bit of a conundrum in that in order to avoid falling through the surface, they have to be water repellent. But then if you're water repellent, you expect not to get such good traction on the free surface, right? Because the things, you have very little contact. So how does it actually work? So it turns out that they use texture. So the texture which I showed you on the leg is known to influence the drag. So you basically get an anisotropy resulting from texture. Okay? So if you look at flow in a Wenzel state, you get drag reduction. So this is a sort of a strange thing, but they scour now airplanes and boats because they find that you reduce the drag by a few percent and you save tons of money. They don't even know how it works. But that's just, so if you have flow, high Reynolds number flow over a surface like this, you actually, if you scour it in the direction of motion, you reduce the drag. It's empirical, so they don't really know why. But this is also true if you're in a Cassie-Baxter state. So if you have a water repellent state, imagine now, so this is, say you have inclusions of air here and water flowing either in that direction or that direction, then the drag is reduced for flow in that direction and increased for flow across. So if there are experiments done by Yoshimitsu, so you basically take a textured surface like this and you put a drop on it, and if the grading's in this direction, it will roll with relative ease with the grading, but with great difficulty across the grading. You can understand this in terms of the difference in the contact line dynamics. Okay? But this is basically used in nature. So here's the wings of a butterfly. When they get hit by a raindrop, they do not want their body cavity to get wet because there are all sorts of sensitive functions there. So they want the drop always to go towards the wing. So they do that, and you can see this. You can see this on the right. Basically, the drops do not want to move in that direction. They always want to go towards the tip, and they do this by virtue. So their wing has a series of scales and the scales are comprised of bundles, right? So this is a blow up of this, and each bundle of fibers has one loose bundle. So as the drop moves in this direction, there's no difficulty, but when it moves in this direction, it gets snagged, and that snagging creates surface area, right? So it's like contact angle hysteresis. You basically get this snagging, and that snagging is sufficient to keep the drop from rolling backwards. So basically it moves with no opposition in this direction and with great opposition in the other direction. So this is why the drops always move towards the wingtip. So it's again using texture to direct droplets. Okay, so we did something similar. So it's a pretty fancy looking thing, but we basically took the leg of a dead water strider and we measured the forces as we moved in the three directions just to see if this had the same sort of anisotropy, and indeed it does. So you have here forces if we move in the three different directions. So it depends on the penetration depth, but generally you have, if you move in this direction, there's very little opposition. In this direction, there's greater opposition, and there's a huge opposition to moving across. Because again, the leg has these hairs which are pointing in that direction. They have this microstructure themselves. So you can see there is an anisotropy, and the sorts of forces you get so it's basically a factor of 2. The largest force being across, then the next one being this, and then it moves with great ease in this direction. So the same anisotropy you see on the leg of a water strider. So you can see if you were to zoom in on the leg as it was taking off, you would see this. This is an end view of a. So just imagine this was flat. So this is basically what you'd see as you drive your leg backwards, and it's the resulting force which is actually giving rise to the propulsion. Okay, and so you can see here, this is the leg of a strider, and we move it back and forth, and you can see that there's anisotropy. It moves relatively easily in that direction, but in this direction there's this huge deformation of the surface, and that's, again, there's an energetic penalty associated with that, and that's why the forces required are larger. So what this means is that as these things glide along the surface, they can move with great ease along their length. So it's like cross-country skis. I guess you guys don't have very good Have you ever cross-country skied? But cross-country skis, they have texture on the bottom, which are like herringbone patterns. So you can glide very easily forwards, but then you can get some traction by pushing backwards, right? So that's what these legs are like. So you can rationalize how this texture is used for propulsion. So basically, by hitting the surface like this, they get a large force, and then they glide very easily in this direction. Right? So here, they're getting maximum thrust, but when they land, they're gliding relatively easily. Okay? So, and again, it's using the geometry. The legs are basically, they're using like a skate blade, but then, and this is because of the texture, so the hair in this direction, but then the hair is also flexible. So we saw the hair, and it's this flexibility which gives rise to the anisotropy in this direction. Right? So the fact that the drops move very easily in that direction, not that one. That one makes them behave more or less like cross-country skis. Okay, and so you can also understand their response to wind. So this is a dead water strider, but you can see it basically turns and always goes with the wind. And this is something you can see if you see a water strider in a stream. It will always point upstream and be able to support itself there while doing very little work. But then if it turns like this, it immediately gets dragged downstream. It's because of the anisotropy in its surface coating. Okay, so this basically provides the rationale for why plants and water-walking insects have different form. So these plants are bumpy. They have to maintain their water repellency. So they don't want to get covered in water because they need to photosynthesize and do other sorts of things, which would be impossible if they were completely wet. And these guys have to stay wet, but they also have to propel themselves on the surface. So this textured surface gives them an additional advantage in terms of propulsion. Okay, and this inspired this so-called bug rug, which was basically an anisotropic surface with flexibility. So you vibrate the thing, and it will move in the direction that the drops are moving, in the direction that the hairs are pointing. Okay, so just before break, we'll just do some miscellaneous things here. So this is some spiders use bubbles, so they basically do an underwater web and trap an air bubble, and so then that'll be their diving chamber, and so then from that they'll go down and go after their prey, and so they won't have to go to the surface each time. They'll basically go for a day with one bubble, go back and breathe, and then no one's really looked carefully at this problem. And then here's another funny one. So this is something we did with. So snails move. This is a snail moving underneath a free surface. So typically you have a snail moving along a rigid surface, and it basically generates lubrication pressures by moving its foot like this. But it's a little more subtle when you're at an interface, because you can't generate tangential stresses there, right? So they do actually rely on capillary forces for propelling themselves along. But it's sort of a kind of a subtle problem. And then there are these bugs that. So these are kind of. This is kind of an open question. These guys, the whirligig beetles, they use it's basically like surface sonar to detect mates and see obstacles and stuff. So they basically move around, and as they do, they're going fast enough that they generate capillary waves upstream, which allows them to basically see the surface. So it's like a bat with a capillary sonar. And then we saw these guys crossing the interface. So how do they do this? I think in order to do this, you can see it's quite difficult, but I think it probably releases a surfactant. I'm not sure. This is what's needed to lay eggs. And then we had this is kind of an interesting one. So you can ask how you generate propulsive force. So these things can jump very high off the surface incredibly quickly, and they do this because they have, again, this one attachment which allows them to clasp the surface, right? So this is basically a hydrophilic region. So they basically grab onto it, and they arch their bodies like this, so you have a force balance, and then they release this. And by releasing that, they throw themselves up in the air. And then, I showed you this mystery before, but I think it's a hoax. So the question is, can these guys actually generate somehow a lateral force to propel themselves along? Seems a little bit dubious, but my students seemed to suggest that they could, but I don't believe it. But these guys are in this position. They're basically grabbing the surface with this organ on their body and appear to be drifting along, but I think it violates too many principles of mechanics. Maybe there was a draft. And this is something that maybe you've seen in Brazil. So ants are not good water walkers, right? So they don't have a water repellent coating, and so they basically get stuck. And this is what things that don't like to walk on water look like when they're trying to walk on water, right? It's slow, it's awkward, and it's unhappy. And so how do ants? So there are many regions where there are lots of ants that get flooded. So it turns out that they go into an ant ball. So the whole colony, in a time of flood, will collect together in a big ball, which is then buoyant. So this object it's like a self-assembling super hydrophobic surface, right? So basically they lock arms and they form this big structure like this. And you think, well, what happens to the guys at the bottom? It's all good for everyone else. But they actually move in such a way that it rotates, and so that the ones at the bottom don't die. So my old student David who did the stuff on walking on water, did a very nice paper on this recently. Okay, so let's take a little break. and we'll get to drinking strategies. I'm going to try and get to the bank. All right.